The Fundamentals of Tool Design video series, examining the diverse field of tool design materials and technologies. This program explores the fundamentals of tool materials. There is a wide variety of tool materials used for cutting, forming, and other manufacturing operations. The selection of a tool material for any given manufacturing operation is normally determined by the mechanical properties necessary for proper use of the tool. Material selection should occur only after careful evaluation of the function and requirements of the proposed tool. For most applications, more than one type of tool material may be satisfactory, with final selection governed by material availability and economic considerations. The principal materials used for tools include ferrous metals, non-ferrous metals, and non-metallic materials. To properly select a tool material, several physical and mechanical properties should be considered to determine how the selected material would affect the tool's performance and capabilities. The physical properties of a material control how the material will react under certain conditions. Physical properties are natural in the material and cannot be permanently altered without changing the composition of the material itself. These physical properties include density, color, electrical conductivity, thermal conductivity, thermal expansion, and melting point. Density is a material's weight per unit volume, such as pounds per cubic foot or kilograms per cubic meter. Besides indicating ease or difficulty of handling, various mechanical properties are often expressed relative to density, such as the expression strength to weight ratio. Color is the natural tint contained throughout a material. Electrical conductivity is a measure of a material's ability to permit the flow of electrical current. Thermal conductivity is a function of how far and how fast heat can flow through a material. Thermal expansion is a measure of the dimensional changes exhibited by a material when exposed to heat, thus affecting accuracy. The melting point indicates the temperature at which a material changes from a solid state to a liquid state. It is a rough measure of heat resistance. Unlike physical properties, mechanical properties can be permanently altered by thermal or mechanical treatment. These mechanical properties include strength, hardness, wear resistance, toughness, brittleness, plasticity, and surface finish. Strength is the ability of a material to resist deformation. It is commonly designated in units of pounds per square inch, or PSI, and megapascals, or MPa. Common types of strength are tensile strength, compressive strength, yield strength, shear strength, and fatigue strength. Tensile strength, also called ultimate tensile strength, is the ratio of the maximum applied tensile load to cross-sectional area to rupture a material. Compressive strength is the ratio of the maximum applied compressive load to cross-sectional area to rupture a material. Yield strength is the stress required to permanently elongate or deform a material a specific amount, commonly 0.2% of total elongation. Yield strength, rather than ultimate tensile strength in tension or compression, is often used as the critical strength for design or structural purpose. Shear strength is the maximum amount of shear load a material can withstand before failure occurs, divided by its cross-sectional area. Fatigue strength is the maximum stress a material can sustain for a specific number of cycles of fully reversed tension to equal compression to cause rupture. The number of sustainable stress cycles prior to failure is the material's fatigue life. Hardness is a material's resistance to indentation and is a measure of its resistance to scratching or abrasion. Material hardness is determined using a variety of tests, the two most common being the Brinell hardness test and the Rockwell hardness test. In the Brinell hardness test, a known load is applied for a given period of time to a specimen surface using a hardened steel or tungsten carbide ball, causing a permanent indentation. Standard ball diameter is 10 millimeters, or approximately 4/10 of an inch. The diameter of the resulting permanent indentation is then measured and converted to a Brinell hardness number. A microscope especially designed for the Brinell hardness test is generally used for diameter indentation measurements. The Rockwell hardness test involves the use of an indenter for penetrating the surface of a material first by applying a minor or initial load and then applying a major or final load under specific conditions. The difference between the minor and major penetration depths is then noted as a hardness value directly from a dial or digital readout. The harder the material, the higher the number. The minor load applied is always 10 kilograms, and the major load may be 60, 100, or 150 kilograms. The most common indenters are either a small 1/16 inch hardened steel ball or a sphericonical diamond, which is also referred to as a Braille indenter. Wear resistance is the material's resistance to abrasion by rubbing, grinding, or other frictional means. The harder the material surface, the greater the wear or abrasion resistance. Toughness is the material's ability to absorb impact energy and deform plastically before fracturing. Toughness is often measured by using two basic types of impact tests: drop weight and pendulum, such as the Sharpie notched bar impact test, and the Izod notched bar impact test. Brittleness is the property of a material that causes it to break or fracture easily with little or no deformation when a sudden load is applied. Plasticity is the material's ability to deform non-elastically without fracture or rupture. Two general categories of plasticity are ductility and malleability. Ductility is the property of a material that allows it to be stretched or drawn using a tensional force without fracture or rupture. Malleability is the property of a material that permits plastic deformation in compression without fracture. Surface finish is the surface roughness of a material. Surface finish influences a tool's quality and service life longevity and directly affects the quality of parts produced from the tool. Tool materials are often coated and/or heat-treated to improve their performance. Thin film coatings are used on a wide variety of tool materials and improve characteristics not obtainable using the tool material alone. These characteristics include surface hardness, wear resistance, friction coefficient, and thermal conductivity. Most coatings are under 1/1000th of an inch or 25/100ths of a millimeter thick and may have several layers. Heat treating processes use controlled heating and cooling cycles to obtain desired metallurgical structures and mechanical properties of metal or alloy tool materials. Heat treating processes can be classified as either through hardening processes that increase the strength and hardness throughout an alloy's cross-section, surface hardening processes that create different properties at the surface than at the center of a metal structure, or softening processes that decrease the hardness of metals and alloys. Ferrous tool materials have iron as a base metal and are widely used for jigs, fixtures, dies, molds, and many other special tools. The primary types of ferrous tool materials include carbon steels, alloy steels, tool steels, and the cast irons. Ferrous tool materials are used in the cast, hot-rolled, cold-rolled, or ground condition. Casting is commonly used to create blanking and forming dies, and sometimes injection molds. Typically, the casting is poured to a rough, oversized form and then is machined to the desired final shape. Hot rolling leaves a layer of decarburized slag on the surface of steel, which must be removed by machining if the steel is to be hardened. Cold-rolled steels have a bright scale-free surface and are rather accurate or close to size. However, the internal stresses developed in cold rolling may cause distortion if extensive machining or welding is required. Ground steels are held to very close tolerances. They are usually used when a finished surface is required without additional machining. They are available ground to size or oversize by 15 thousandths of an inch or 38 hundredths of a millimeter above a standard size. Carbon steels contain mostly iron and carbon, with small amounts of other alloying elements, and are used extensively in tool and jig construction. Carbon steel grades are designated as low carbon, containing between 0.05 and 0.3% carbon, medium carbon, containing between 0.3 and 0.7% carbon, and high carbon, containing between 0.7 and 1.5% carbon. Alloy steels are basically carbon steels with additional elements added to alter their characteristics and bring about predictable change in mechanical properties. The alloying elements used most often in steels are manganese, silicon, nickel, molybdenum, and chromium. Alloy steels include the corrosion-resistant stainless steels, which are high chromium and nickel chromium steels. Some high chromium stainless steels can be hardened by heat treating and are used for tools requiring resistance to high temperature, wear, abrasion, and corrosion, such as plastic injection molds. Tool steels are generally high carbon, high strength alloys modified with other alloying elements to produce steels having varying degrees of heat resistance, abrasion resistance, shock resistance, dimensional stability and hardening, and cutting ability. Because no single steel can optimally possess all of these properties, hundreds of different tool steels have been developed to meet the vast range of service demands. The American Iron and Steel Institute Tool Steel Classification System uses a letter and number designation to identify and classify the materials in the 7 major families of tool steels: water hardening steels, cold work steels, shock resisting steels, high speed steels, hot work steels, plastic mold steels, and special purpose steels. Water hardening tool steels are essentially high carbon, plain carbon steels and account for a large percentage of all tool steels used. Water hardening tool steels are available as shallow, medium, or deep hardened, and are capable of Rockwell C65 to C67 surface hardness. They are the least expensive and most readily machinable tool steels. Applications include blanking dies, forming dies, drills, countersinks, reamers, taps, and files. Cold work tool steels incorporate various amounts of manganese, silicon, molybdenum, and chromium alloying elements, and are used in applications where improved toughness is required. There are 3 basic kinds of cold work tool steels: the oil hardening, the air hardening medium alloy, and the high carbon, high chromium grades. Because of their alloy additions, the oil and air hardening tool steels maintain high hardenability while providing the best freedom from distortion and cracking during heat treating. This is due in part to their slow cooling rates. Applications include cold forming, corning and burnishing tools, as well as molds, shearing knives and blades, and rotary cutting knives. The high-carbon, high-chromium tool steels contain between 10 and 18% chromium. When heat-treated, these steels are best in hot hardness and wear resistance applications, such as forging dies, die casting die blocks, and drawing dies. Shock-resisting tool steels contain less carbon and provide higher toughness for both hot and cold impact applications. Carbide-forming alloys provide the necessary hot work, abrasion-resistant, and hardenability characteristics. The high-speed tool steels are used for cutting tools and other applications requiring strength and hardness at sustained temperatures up to or exceeding 1400 degrees Fahrenheit or 760 degrees Celsius. There are two primary grades of high-speed tool steels, tungsten and molybdenum. All are high alloy steels, hardenable to at least Rockwell C63, some to Rockwell C70, and possess fine grain size and uniform deep hardening. All high-speed tool steels contain some tungsten, chromium, and vanadium. Most also contain substantial cobalt. Hot work tool steels provide good wear resistance, shock resistance, and high hardness during prolonged use at elevated temperature. All hot work tool steels employ substantial carbide-forming alloy additions of chromium, tungsten, and/or molybdenum. These steels are generally preferred for extrusion tools, die casting dies, and forging dies. Plastic mold tool steels are tough oil-hardening grades that are rather low in carbon content and wear resistance. These steels are designed to meet the requirements of zinc die casting, plastic injection, and compression molding. Special purpose tool steels are limited in use but feature good toughness and machinability. Special purpose tool steel uses include press brake dies, punches, and taps. Cast iron is essentially an alloy of iron containing from 2 to 4% carbon, 0.5 to 3% silicon, 0.4 to 1% manganese, plus phosphorus and sulfur. Other alloying elements may be added depending on the properties desired. The carbon in cast iron occurs in two forms: graphite or free carbon and iron carbide or cementite. The high carbon content makes molten iron fluid, easing castability. Graphite increases casting soundness, machinability, damping quality, and lubricity. Cast irons are not usually specified by composition, but by grades, classified by minimum tensile strength. The principal grades of cast iron include gray iron, ductile or nodular iron, compacted graphite iron, malleable iron, white iron, and alloy iron. Non-ferrous tool materials have a base metal other than iron. These tool materials are utilized to some degree in mold and die-making applications and find common use in jig and fixture design where magnetism and tool weight are factors. Non-ferrous materials and their alloys are also extensively used for cutting tools to machine high-strength materials. The three most common non-ferrous tool materials are aluminum, carbide, and cermet. Aluminum has long been used for special tooling such as thermoforming molds. The principal advantages to using aluminum are its high strength-to-weight ratio, non-magnetic properties, and relative ease in machining and forming. Pure aluminum is corrosion resistant but not well suited for tooling. Aluminum alloys, while not as corrosion resistant as pure aluminum, are much stronger and commonly used for tooling applications. Carbide, which is also referred to as cemented carbide, is a powder metallurgy product made of finely ball-milled or processed hard carbide particles, bonded together by a metal binder. The hard carbides include tungsten carbide, titanium carbide, tantalum carbide, and niobium carbide. The hard carbide particles are submicron to 10 microns in size and make up from 60 to 97% of the material. The binder is mostly cobalt. 2/3 of all carbide tools used are coated. In general, a coated carbide tool may have over 3 times the tool life of an uncoated grade, or may be used at cutting speeds 2 to 4 times faster for the same tool life. The primary cutting tool coating materials are titanium carbide, titanium nitride, aluminum oxide, titanium carbonitride, titanium aluminum nitride, and combinations of some of these. Tough shock-resistant carbide grades are needed for interrupted cutting. Harder and chemically stable grades are needed for finishing steel at high speed. Tough and heat-resistant grades are needed for machining the superalloys, such as Inconel and Hastelloy. Carbide is used for solid round tools, such as drills and end mills, or in the form of cutting tool inserts. A surmet consists of hard material, such as titanium carbide or titanium nitride, and a nickel or cobalt binder. The solid surmet cutting tool insert offers excellent surface finish. Initially used only for semi-finish and finish turning and boring, some surmet grades are now tough enough to handle rough turning as well as milling applications on carbon steels, stainless steels, and some ductile irons. Non-metallic tool materials are used mainly for limited parts production and where the cost of using tool steels and other materials are not economically practical. Non-metallic tool materials can be used by themselves to create special tools, but commonly incorporate metallic elements. Some of the principal non-metallic tool materials include wood, composites, rubber, ceramics, diamond, and cubic boron nitride. Wood is often used in low-cost, limited production tools. Some common applications include short-run or prototype thermoforming molds, steel rule dies in which wood supports the rule, and jig plates with inserted steel bushings. There are several varieties of wood products used in tooling applications, including hardboard, densified wood, particle board, and plywood. Composite tool materials consist of a reinforcing material and a matrix or base material. The matrix functions as a binder for the reinforcement and controls the physical shape and dimensions of the tooling. Special composite tooling materials are used as economical alternatives to metal tooling for composites manufacturing. Additionally, composite tooling is desirable since it can have the same thermal expansion characteristics as the composite parts being manufactured and cured. Composite molds are usually backed by stiffeners to give additional rigidity to the critical mold dimensions. These stiffeners can be metal, composite, or even wood. Rubber is used in special drawing, blanking, and bulging die operations, as well as for protective elements and other special tools. Silicone rubber, specifically RTV or room temperature vulcanizing silicone, is used as a rapid means of producing soft tooling for low pressure molding. A pattern is used to create the RTV mold halves and pattern cavity. Once prepared, this tooling can be used to mold small to medium quantities of parts from various urethane, epoxy, or other polymer materials. RTV tooling can typically be used to mold several parts before replacement becomes necessary. The number of parts produced depends on accuracy and finish requirements and the complexity of part geometry. Ceramic tools have high compressive strength, high hot hardness, high resistance to abrasion and galling, and low heat conductivity. They are used primarily as high-speed cutting tools to machine extremely hard or highly abrasive materials. Ceramic cutting tools can be divided into alumina-based ceramics and silicon nitride-based ceramics. Standard alumina-based ceramics are used for high-speed semi-finishing and finishing of ferrous and some non-ferrous materials. These tools are not good with aluminum because of an affinity between the materials. Alumina-based ceramics offer good mechanical and chemical wear resistance, but lack toughness and thermal shock resistance. Thus, they are generally not used for milling, rough turning, or for interrupted cutting. Silicon nitride-based ceramics, sometimes called Sialons, offer greater toughness and thermal shock resistance than most alumina-based ceramics. They are used in high-speed roughing applications where excellent abrasion resistance is required. Silicon nitride-based ceramics are used for high-speed machining of gray cast iron as well as superalloys such as nickel and cobalt-based materials. Whisker-reinforced ceramics with silicon carbide reinforcing whiskers in an aluminum oxide matrix are stronger than the brittle ceramic matrix alone. The whiskers act like rebar in concrete, adding mechanical strength and thermal shock resistance. Diamond, synthetic or natural, is the hardest of materials and finds limited use as a tool material. It is used for turning and milling tools, grinding wheels, and grinding wheel dressers. Diamond powder-coated tools are used for lapping and polishing operations and can provide very smooth and lustrous finishes. Polycrystalline diamond, or PCD blanks, consist of micro-sized diamond particles in a metallic binder and is more than 50 times harder than common carbide. Polycrystalline diamond blanks are used either as indexable inserts or are brazed to a cutting tool. They machine non-ferrous and non-metallic materials, but because of their high chemical affinity to carbon, cannot be used on ferrous materials. Cubic boron nitride, or CBN, is the second hardest material after diamond. It has a compressive strength of 700,000 psi, or 4,830 megapascals, twice the thermal conductivity of copper, and is thermally stable and oxidation resistant in air to about 3,500 degrees Fahrenheit or 1,925 degrees Celsius. Used for grinding wheels and cutting tools, CBN is used to machine ferrous and non-ferrous metals that cannot be readily cut by more common materials.